Next up, how do we actually look at these reactions? So whenever you do kinetic analyses of a substrate, you determine rates at various different concentrations of that substrate. And so when substrate concentration is less than your Km, so you're going to give a range from substrate concentration less than your Km to significantly greater than your Km. So to make a bisubstrate reaction perform like a unisubstrate reaction, we keep the concentration of one substrate at saturation while studying the effects of the other substrate. So essentially what that boils down to, or the way that I kind of look at that boiling down to something, is you have, let's say we have substrate A and B. Well, you have a Km for substrate A, and you have a unique Km, so let's just call this like 3 millimolar. Well, substrate B, that might be a Km of 0.0001 micromolar. That's still relevant. You still have to know what that concentration is to get you to half of B max, but that's something that is worth noting. So when you're studying a particular substrate, in this case, if we're studying substrate A, we're going to have substrate B at saturating conditions or at saturating concentrations. Then what you do is basically the opposite. So you would study you would saturate with substrate A, and you would you would vary the concentration of substrate B. When it comes to substrate addition and product release, well, we basically have this fall into two different categories. So this is all about the sequence of particular substrates. So when we were talking about the ethanol and NAD+, well, what happens first? Does the NAD+ bind and then the ethanol bind, or vice versa? Or does it even matter? So the order of substrate addition and product release in most enzymatic reactions is going to basically follow these two different reaction mechanisms. One of them is a sequential reaction, in which all substrates must bind to the enzyme before the reaction occurs and products are released. So we'll look at what that actually kind of looks like in a schematic in just a moment. The alternative is, well, a ping-pong reaction, in which case one or more products are released before all of those substrates have been added, and an alternative stable form of that enzyme, characterized as F or labeled as F, I'm going to put that in quotations right here, is produced in that half reaction, or in a half reaction. Okay, so I think that it's a little bit more clear whenever you look at kind of the layout for what this actually looks like. So in a sequential reaction, all of the substrates must bind to the enzyme before the reaction actually occurs and products are released. Okay, so here's our rundown. I'm going to start over here at the left. What we have is kind of the timeline of a reaction. This is our zero time point, and then I'm just going to call this our finish. Okay, so we start out with our free enzyme present. Okay, what happens is that free enzyme binds our first substrate, A. We form an EA complex. Okay, once that EA complex has been formed, well then we can have substrate B bind. Maybe I shouldn't have used a red highlighter to highlight a red letter. At any rate, substrate B can bind. Well, whenever substrate B binds, then we can form this we have formed this EAB complex. That is the entire complex with the enzyme bound to both of the substrates, and it is ready to go. And with that, we form, a reaction takes place, and we form our two products, P and Q. Okay, so it doesn't really matter which reactant, or does A become P and B, or B become P? It doesn't really matter. The point is, and that's going to be variable for any and every reaction, but the point of this is that as soon as your reaction has bound to, your enzyme has bound those two different substrates, well then everything's ready to go. And you can release one product, you're left with the EQ, then you can release your second product, and then lo and behold, your enzyme's ready to go, and boom, you can continue on catalyzing that reaction. Okay, now, alternative to this is, there's your, I put that as chemistry just because that's where your reaction is actually taking place. Now let me go ahead and erase this because there's a little bit more that you can qualify all this information with, or you can do a little bit better definition or defining of it. In an ordered sequential reaction, you have a necessary order. So in this case, up here, where I've just drawn a blob, A has to bind in order to form EA, which then enables B to bind. Okay, so in this particular case, B would not bind before A because this is an ordered sequential reaction. Okay, you can also have an enzyme that has a random sequential reaction. So that is one in which the reaction shows no preferred order of your substrate addition or your product release. Okay, so what that would look like would be something like this. Your enzyme, and this is totally random. So let's say in the first time that this enzyme catalyzes the reaction, well, it could go the direction of binding A. Once EA forms, then you could form that EAB complex and then go on, catalyze the reaction. And then maybe what happens is, well, the first product that's released is Q, then the second product that's released is P. Okay, now the second time through, maybe what happens, and I'm going to change the color that I'm using to blue. Now what happens is maybe E binds B, then then EB binds A, and then, well, heck, maybe then, after the reaction has taken place right here, well, then Q is released, and then P is released. Okay, so this is a random sequential reaction where it doesn't really matter what actually happens in terms of a sequence. Okay, so the alternative to that is the ping-pong reaction, in which one or more products are released before all substrates have been added, and an alternative stable enzyme form F is produced in that half reaction. Okay, so I'm going to go ahead and say that in this case, the free enzyme has to bind A. EA, well, that is going to be a scenario where a reaction takes place. Your first product is generated. Okay, so your enzyme, your E, it binds to A reaction has taken place, and now the enzyme is a new form. It's the F form. If you wanted to, you could think about it as maybe something like F is equal, and I always think about this as F is equal to E with a phosphate. So it's a phosphorylated form of the enzyme. It's not necessarily radically different, but it's now added a phosphate group. So maybe your A molecule is ATP, okay, and then P is ADP. So adenosine triphosphate, adenosine diphosphate. So maybe what happened was a phosphate group from here was transferred onto your free enzyme, forming that phosphorylated enzyme, or your F, or also known as your F molecule. Okay, ADP has been released, and now we're dealing with the phosphorylated form of our enzyme, which can bind our second substrate, B, forming the FB form, and we can return to EQ, or sorry, we can have some reaction take place where Q has been modified, and now we're back to our original form of our enzyme. So the reason I always like to think about this as a phosphorylation event is because it makes sense to me where you could have your EP, our phosphorylated form of our enzyme, binds to B, and then maybe what happens is Q is the phosphorylated form of B. Or let me erase that. Q is equal to phosphorylated form of B. Oh, that wasn't drawn very well. Okay. But this is basically what we have taking place here, where we have a unique form of our enzyme as an intermediate that causes our reaction to take place. So what that means is, in a ping-pong reaction, could E bind to A? No, it couldn't, because F is the form of the enzyme that has a strong affinity for molecule B. So you're never going to see, in a ping-pong reaction, E bind to B. You're going to see E bind to A, reaction takes place, F is produced, F binds to B, E is returned, Q is released, E is now ready to bind to A again. Okay, so almost always the modified form of an enzyme has formed a covalent bond to that substrate. Okay, so that would be a good example of a phosphate bond, or maybe you'd have like a potentially a sulfur-sulfur bond or something like that along the way. All right, well, I hope that was helpful. Thank you very much. Have a good one.